Good morning. It's January 7th, 2024. Ross Finlayson here in Moment and Motion for the philosophical foreground bit. This morning, what I thought I'd do is kind of talk about descriptive waves, because a wave is a very general concept of any kind of propagation of change in a closed or open system. It essentially it is the open system. And so with regards to then all the various kinds of waves, we enter a sort of descriptive framework where what gets relevant is to make it so that we have a sort of series of descriptions which then reflect for what we have as the concept, and then for the formalism that the descriptions become qualitative and as well quantitative, where the goal is to achieve a sort of well-defined overall kind of milieu and framework for what are waves. And in so regards that, then there's been a reading from Colson's waves from the university texts, which were kind of the curriculum of the honors course, as it were, in the UK and US in the times of the mid-20th century and all that kind of stuff. And then with regards to kind of a more modern day approach is to take some reading from Mogan and Braikovsky, kind of their descriptive accounts of waves, and with regards to waves in layered media, waves in homogeneous media, waves in planes, waves on surfaces or about surfaces, waves as just any kind of notion of what's the linear impulse, so carried or the carriage, or waves as the expanding wave or radiation, with regards to any of these interfaces, or what are closed systems in physics to a more open system in physics, or outside the boundaries, is the notions of the radiation of waves, where radiation is a usual most general concept of going out and about as the radial, these kinds of things. So first, here's a little book called Viscoelastic Solids, and so this is kind of for the material science and the engineering and also the science of it. So Roderick Lake's Viscoelastic Solids is a sort of from the CRC, the Chemical Rubber Company Press, Mechanical Engineering Series. There's the CRC press is really one of those famous marks, and why they're so important, and usually or often that people become familiar with it, is the CRC press handbooks, which basically are the tomes, kind of like the automotive handbook was for an introduction to the surface of what gets into a mechanical engineering for motor vehicles and automobiles. Is that the CRC press handbook, and I have one, is a very, very valued tome, and kind of what would be like, this is the only book you'll find in the entire lab. So this book then talks about a one-semester graduate course in the theory, and he talks about the phenomena, predictions of response of the linearly viscoelastic materials, and then he introduces some descriptive terms like creep and relaxation, stress versus strain, constant strain, creep and relaxation, these being the descriptive milieu of what is, for this theory, of these kinds of objects and their elements would have the properties of disparate things, that they're trying to figure out how they kind of go together, and overall this theory of continuum mechanics and all this kind of stuff. Gets into Kramer's Kronig relations, energy storage and dissipation, resonance of structural members. This is into the dynamic behavior. So it starts with constitutive relations and then gets into dynamics of these materials, and he talks about what we have for like the linear and what's kind of directly computable. And then getting in the dynamic, which is, it affects these running constants and when things change. And so then it gets into a conceptual structure of linear viscoelasticity, and then to deformation analysis and these kinds of things, where the general notion is that There's the non-deformable and the deformable. There's the non-adiabatic and the adiabatic. There's elastic and inelastic, and all these sorts of notions, which get into like the compressible and incompressible, vis-a-vis all these sorts of models, like the fluid models and the gas models and the models of solids and crystals and all these kinds of things, which affect basically a wide descriptive milieu of the necessary vocabulary and lexicon to be able to comprehend thoroughly these things, and then is addressing them qualitatively to reach to the quantitatively. I haven't really studied this book, but he gets into many properties of materials like polymers, metals, rock and ceramics, concrete, asphalt, ice, piezoelectric materials, biological materials, porous, composite, inorganic, amorphous materials, and common aspects. Then he talks about causal mechanisms, and this is the usual notion of what is indicating a gradient, or what, according to least action, will so carry, what's causal, and so deterministic in such a manner in this theory. And then into these composite materials, applications and case studies. And then the appendices include mathematical preliminaries of functionals and distributions, transforms, Laplace transforms, which gets into our whole notion of the harmonics and theory of potentials, and whether or not it's sufficient to say that the study of harmonic functions is a theory of potentials, or that it's just briefly a partial milieu. Concepts for dynamic aspects, phase determination by subtraction, and interrelations in elasticity theory. So, briefly, I just wanted to point out that this gets in a lot of these different same kinds of aspects for this whole kind of section of the field. What with regards to having common language and a dialect and a lexicon and a vocabulary and the relations and everything square, it helps reflect that for such marks as these, that they have a lot going on, and it's so necessary, and that it's as well that there's the common subset of these that are useful in all these different milieu, that are above our foundations, is then basically the language of mathematical science and engineering for practicing physicists and engineers in usual sorts methods. Resonance methods, page 200. General principles. Here, this is for the wave theory, above wave theory, over particle wave duality, or resonances. These are the higher order harmonics, the overtones, and these kinds of things that really get a lot into what are the issues related to what we want to get figured out. Resonance methods are eminently suitable for low-loss materials. By contrast, small tangent delta values are difficult to measure in the subresonant domain. The resonant behavior of materials with small tangent delta 10 to the negative third and 10 to the negative 6 differs dramatically, as we have seen in section 3.5. So I had started reading this, and he helps establish particularly that their dynamical effects start to come into play on several orders of magnitude, not necessarily like 20 orders of magnitude, 30 orders of magnitude, but real dynamical effects start to take place within only a few orders of magnitude in many of these sorts of systems, with regards to what are the impulses, then the linear, and with regards to the milieu and the aggregates in the bulk. And as for the forces and couplings of stresses and strains, with regards to these interfaces, as are generally considered what's called classical. Resonances in tension, compression, torsion, or bending. For the half-width, delta omega. And for damping from the free decay time, T of 1 over E, T sub 1 over E, vibration of period T. These relations are valid for small tangent delta. As for the specimen stiffness, it is inferred from the resonance frequency V naught in conjunction with the specimen geometry. Observe that in the resonance scheme, there is no need to measure the force of torque, but if it is not measured, it must have constant amplitude over the frequency range associated with the resonance peak. here it's talking about what's fixed and free with regards to, much like when we were reading Mogan's nonlinear electromechanical effects and applications, that it's about these parasitic phenomena and what's regarded as what should be held fixed or free with regards to otherwise that being on the ridge, as for the gradient, that these effects would just be lost in the noise. So this is just an example that for fixed free configuration and free configuration that he gets into the mechanical torsion for free resonance methods and fixed free approaches, particular resonance methods, and then also as with regards to in the waves, then again, how we talk about the near field and far field with regards to this oscillative and restitutive of the constitutive and the attenuative and the dissipative of the deconstitutive. Yeah, I'd started reading this, and I'll get back to it because it really helps to affect an awareness of a lot of the concepts and the language of the dynamics. This book isn't so much relevant to what we're talking about in a moment of motion. It's Norvig and Russell's artificial intelligence. It's about it. What it is it's basically it's about 1,400 pages. Well, not that many. It's about 1,000 pages, and what it gets into is various notions of the neural nets and what goes on into various kinds of statements of logic and inference in what we call the quasi-modal logic, because it's very highly based on what you call the classical quasi-modal logic, and with regards to then it implements various simple forms given facts and inputs as with regards to what rules that basically details how to design a big thinking machine that kind of runs at a very high scale, at a very simply in a lot of its fundamental and elementary terms, and it also kinds of details how that last wins. And so basically what you can do is take the whole body of knowledge and give it a fact at the end, and it'll say whatever you want. So it kind of details an approach, and a very common approach, which you can find a lot these days. For example, is implemented in the wide thinking mind of the usual sort, and but it doesn't really so much detail more richly the entire trifecta of logic implemented properly, quite thoroughly, which aren't necessarily the fastest or most optimal things when pick 2 out of 3, fast, cheap, or right, but it does kind of detail how to do stuff fast and cheap. All right then. So what we hope to do today is find some notions of descriptive waves. So waves and layered medias from academic press, another great kind of mark, something that you can trust from the publishers, because this is considered the top line of academic output. Stuff like CRC Press, AP. World Scientific is considered a great technical imprint of the publishing. So, other volumes in this, it's a part of a series, an international series of monographs, include Oswatich's gas dynamics, Burkhoff and Zarantonello jet wakes and cavities. So that gets in a lot of stuff with the waves in fluid models combined with gas models, the incompressible and the compressible, vis-a-vis flow and direct flow and what we might consider as wash flow, or that kind of when we're talking about the magic squares and how it's possible to so consider where we have most of our models, like from the heat equation for like it's just linear flow, and it's very uniform across the surface, and it's always one direction, vis-a-vis all the ripples and eddies, what should make for this wash flow, which gets into basically these days what's called the adiabatic and the non-adiabatic. Theory of compressible fluid flow. Electronic digital computers, their use in science and engineering, 1958. So some of these texts in an international series of monographs called Applied Mathematics and Mechanics are from the 50s here. Hayes and Probstein's hypersonic flow theory. Berkovsky, Waves and Layers Media. That's this book. Torques, 1960. Singer's Torques and Altitude Sensing in Earth Satellites. Van Dyke's Perturbation Methods in Fluid Mechanics. So this is one of these notions of how to go from the linear flow to the wash flow, is these perturbative methods and methods of small perturbations, for the random motion, and otherwise the minima and maxima are local, but also end up being in some of the mathematical methods and treatments having gimbal lock or otherwise getting stuck. And so these are the methods that help just kind of like oscillate it a bit with regards to then it will reach a more global minimum or maximum. Otherwise not get stuck. Miele's theory of optimum aerodynamic shapes. So optimum means to achieve via constraints, which what is possible and what has to trade off. That which for a particular quantity is of a maximum or minimum, optimum. And so for aerodynamic shapes is what you might imagine they have two roles to fulfill. One is lift and the other is not drag. So Bechoffen Criminal's stability of parallel flows. So the parallel and laminar flows help reflect that, as we kind of have waves as anything moving, but the flows as a surface, kind of like a river, and then the laminar is in the layers that we have our waves and layered media, that this is about laminar flows, or here parallel flows. Berger's flow equations for composite gases. Lumley's stochastic tools in turbulence. So now this series is up to 1970. They don't really emit books so very often, but when they do, it's kind of a big deal in their series. Theoretical magnetofluid dynamics. So this gets in regards to the rheological and these days, for example, people are familiar with shock absorbers that use rheological magnetohydrodynamic effects, and these kinds of things that basically use the electrical properties of particular substances to set it up that can affect the stiffness and give for something like the shock absorber or otherwise the interface between a highly dynamic medium like the road and the wheels on it and the car that is in motion. Introduction to singular perturbations. So O'Malley's 1974, you might expect to find in it how to talk about, here as we talk about like Lefschetz and singularity theory and multiplicity theory from algebraic geometry, how to get figured out, all these kinds of things that help make for that a singularity is a multiplicity. It's just a branch of a multiplicity. And so trying to figure out then how the goes back apart and comes back together is a lot of these different kinds of things. They get into dynamics, analysis of turbulent boundary layers, waves and layer media. Oh, so this is this second edition. So the first edition was 1960, and this edition is 1980. Stratified flows, Yee's stratified flows, 1980. So as you might imagine, these sorts of theories are considered necessary to have a kind of thorough understanding for such things as submarines and airplanes and boats. of the very modern, and with regards to the extremes in milieu. All right, waves. Some applications waves. So this book starts right at the beginning with these waves, and I mean, it's just the general discourse, and any kind of course in these kinds of things would start to lay out what it is. Plane waves in homogeneous unbounded media. A plane wave represents the simplest form of a wave motion. The most general analytic expression for such a wave is f of n sub xx plus n sub yy plus n sub zz, all that over c. All that minus t. So the parameter is as reflecting a negative in t for time, and the other is these three space dimensions, and each one a coefficient as of over c, that this reflects on Coulson's forms that we already kind of read on, and we'll kind of so carry on this way, where the coefficients are three numbers satisfying the condition that their sum of their squares equals 1. So this gets into this whole identity dimension bit is in just a matter of reflection. And our projections on the coordinate axes of the unit vector are normal to the wave front, i.e. to the plane on which the argument of the function in 1, 1 remains a constant. Planes of constant phase. The function is a solution of the wave equation grad squared f minus this quantity. So that's the gradient is the steepest descent, or it's basically its principal line, which indicates either up or down how it is and where it is. That a singularity would be 0, like the tidal, like the spiral, like the vorticial, or the still pool. Delta squared, grad squared f minus 1 over c squared, d squared f, that the function above, over dt squared equals 0. So this is the this is the differential equation. These are our integral and differential equations. And this is one of the constraints, and the other one is grad squared is on the order of the sum of the second partials of the raw differential of each of the bases. So that just defines gradient in that way. But you can imagine that gradient could be defined more as about from the corners of the cube. This is something that's usually kind of left out of harmonic function theory in the Laplacian, because it's not the linear part. These are otherwise just the partial linear parts. It describes some disturbance which is propagated with a velocity c. So this basically reflects, as regards to the wave number, its period. The form of the wave, defined by the form of f, remains unchanged during propagation. So this indicates that there's no loss to this wave. It does not radiate or lose energy at all. Whatever it is, its so carriage, according to its inputs and outputs, is as 0. The so-called spectral method of investigation of wave and oscillatory phenomena is widely used in physics and engineering. We shall also use it in what follows. This method allows us to reduce the analysis of the behavior of the waves of very arbitrary form in cases in which the superposition principle holds to the analysis of very simple harmonic waves. So this helps reflect, the entire great facility of Sturm-Liouville in the differential analysis, and that this superposition of solutions is any one of which can add up to be a solutions, then is according to initial conditions, that what results, then you plug in numbers and get out one of those that happens to match. After, for example, an eigensystem approach. It's bog standard. It's common knowledge. So everybody has to sit through linear algebra, and everybody has to sit through vector spaces. Everybody has to have these theories of waves, and everybody has to have these theories of the differential analysis, just to get to draw on this plane line and having it be formulated so far. Then all these different things get into, for example, from the book on the nonlinear applications in PDEs, all these different things, the world of dynamical methods, the world of dynamical modeling. As, for example, when we read from Stefani about Lie symmetries and his introduction declaring that, there are some things that everybody knows and all kinds of things that become where what we want to have is a milieu, like the descriptive differential dynamics, where it's all kind of put together, and then as well, especially that there's all these nonlinear aspects, all these different perspectives for all these different projections of any such manner of dynamics reflects still a unified sort course. And here he says that at least everybody has this part. To the analysis of very simple, harmonic, and he puts that in quotes, waves. Why the author put this word in quotes is something to be said, and as to whether he means more or less, or simply is the overdefined or the underdefined. So he says we have a notation of epsilon equals the sum of the components, the space components by their coefficients, all that over c, this wave number, minus t, and he calls that epsilon. And represent the function f epsilon as the real part of the Fourier integral. So here we kind of studied the Fourier-style analysis. He says of the Fourier integral, f epsilon equals the real part, the integral from 0 to infinity of psi omega times e to the I omega epsilon d omega. So this whole idea of the Gaussian analysis after the Eulerian identity and its applicability for infinite series for analyticity is something that kind of deserves a very regular sort of re-examination, a revisiting, because it's well, at the same time then it becomes simple and closed form, and it's written as what's called linear or what, just because the identity is kind of not really examined in all cases, that it's just kind of the principal Gaussian branch, and it ends up giving a lot of these other identities that then become very tractable, is that it's something to be said that the Gaussian and Eulerian complex analysis is not the only way to achieve such routes, and as well it may obscure somewhat or other more relevant and necessary things to make it so that there's a fuller complement of definition to arrive at more of the needful for these kinds of things. Since the root part of an arbitrary complex number can be written in the form real A equals A plus A star quantity over 2, then the f of this epsilon equals 1/2, and this is cool because it gets into doubling and halving spaces, and then for addition formula, this sum of these two terms, the first one being 1/2, the integral from 0 to infinity. So as of the area underneath this function all the way out to infinity from 0, the half plane, the semi-plane of this psi omega e to the I omega epsilon. This is where it's this self-parameterized, differential system of accords to the quantities. This was discussed quite thoroughly in descriptive differential dynamics. D omega, that being the phase angle usually, or the angle, plus this other quantity, but instead of psi, it's psi star, and instead of e to the I omega epsilon, it's e to the negative I omega epsilon. So in this manner, it's a simple matter of reflections and rotations about the even and odd, which help effect a relay that it's kind of these two halves put back together, that it's a sort of analysis, kind of like the idea of the hyperbolic hat analysis, compute half of it and then just double that, because it's easy to compute this one on out to infinity, while the asymptote that came down to it is kind of not a real function yet. It results this form. It's a form. Multiply its expression by e to the negative I omega prime epsilon d epsilon and integrate over epsilon from negative infinity to infinity. It is then not difficult to obtain the following for the spectral density function. That's psi of omega equals 1 over pi, integral from negative infinity to infinity, f of epsilon e to the negative I omega epsilon d epsilon. So this trace, or this indicator, the significand of what comes out of this these terms, these constants that basically are the parameters, ends up being then derived and built as to a quantity that then, according to all these things that go into it, why then it can be treated algebraically, canceled and struck, or combined and treated in powers and roots and objects otherwise of arithmetic and algebra, to have it kind of very, very carefully all tented up on this way, vis-a-vis the circus tent, the high wire act, and the safety net, which doesn't exist. Spectral density function. The integrand in this f of epsilon, which corresponds to a certain value of omega, he says, okay, so omega is f of omega xyz has to be so that psi of omega e to the I omega epsilon equals psi omega to this function e to this quantity I to the omega this times this quantity, the sum of the terms by their coefficients over c, all that minus t, where this way the space-like and time-like for the Galilean invariant is kind of just so carried in this manner that it has for a given time, it's got this distance, and for this distance it's got this time. And this is how they come together this way, because they balance. All parameterized by time is a plane harmonic wave. Here we use the complex form of writing both the Fourier integral and the expression for the individual harmonic wave. It is necessary to give physical meaning only to the real part of the corresponding expressions. Here again, as usual in matters of style, when somebody says it is necessary, I wonder whether they mean there's no other way, or other ways break it. It's kind of both. Whereas in logic, of course, it's quite entirely unambiguous, correctly stated, to say something is or is necessarily, or is not necessarily, or is necessarily not, as those different things, each particular to relation and predicate. Therefore, in the final analysis, the harmonic plane wave should be written in the form of the real part of equation 1.5, this definition of omega, the angle, i.e. a of omega and times cosine of all this, and so this being for the Fourier coefficients and style analysis, the term of the sum of the coefficients and the coordinates in the space, all that quantity, times omega over c, so that the usual quantity of the coefficient in the terms in the space over c times omega minus omega t, so basically the usual term of the sum of the coefficients in the space over c, all that minus t, all that times omega plus phi of omega. Little psi, sorry, that's not phi, that's little psi. Here we have represented the generally complex function big psi omega in the transition in the form big psi omega equals a to the omega e to the I little psi omega. The following notation is standard. Omega over c equals k equals 2 pi over lambda This is familiar from reading from the definition of waves. These are the numbers. These are from Coulson. What are all these invariants and all the formulas which will follow? Kn sub x equals k sub x, Kn sub y equals k sub y, Kn sub z equals k sub z. About where k sub x, k sub y, k sub z are the modulus of the wave vector, wave number. Here, Braikovsky introduces that for the wave number, we also have is where it's a wave vector. So that can be very interesting to consider when it says with regards to the multiplicity theory, when it's something that is otherwise a little linear, has higher order, or the multipole. That's what I'm reading into it. And its components along the coordinate axes respectively, and lambda is the wavelength. Then equation 1.5, which is this function that defines omega, is rewritten in the form f equals big psi omega e to this quantity I times these k. Now the k is the coefficients minus omega t. So it's still in terms of omega and c. It's just rewritten in terms of the numbers, the wave numbers, equals big psi omega e to the I times vector k dot vector little r for radius usually minus omega t. Since the differentiation of a function such as f with respect to t reduces to its multiplication by negative I omega, so that's interesting. The wave equation for f can be written in the form grad squared f plus k squared f equals 0. Since the differentiation of a function such as f, this form, with respect to t, reduces to its multiplication by I omega, negative I omega, the wave equation for f can be written in the form. The following features of the spectral approach have led to its widespread application to wave phenomena. So this after the Fourier-style analysis, which is kind of read into, and for the Eulerian and Gaussian and their complex analysis, not the Cartesian with reflections and rotations and all the hypergeometric algebra that model rotations as products of simply as after roots of unity and those great things, but the Eulerian Gaussian that goes out is after e to the I pi equals -1, and its relation to an infinite series of these things and how it's brought in and about and used in the telescoping and the scaffolding for Fourier-style analysis. That this is then used to build up and out what's called a spectral analysis, where the spectral has a lot going on with the continuous and discrete, and with regards to back and forth from the spectral lines vis-a-vis what's radiation in these continuous wave phenomena. All waves are essentially continuous things vis-a-vis their sonons and phonons and these descriptive elements in the model of them as particles, and the conceit is as to what they are. That this is describing basically the framework and the intent of these concepts that come together to help make it so that then carrying forward, he can express all such manners of these kinds of things in these terms. The following features of the spectral approach have led to its widespread application to wave phenomena. 1, the comparative simplicity of analysis of the behavior of each of the harmonic waves. It's tractable. Well, it's fungible, at least, and then with regards to, and it's tractable because then we use Sturm-Liouville for everything. 2, the possibility of expansion of an arbitrary wave process into harmonic waves in cases in which the superposition principle is valid. 3, the very high monochromaticity of many radiators used in practice, as a consequence of which the waves radiated by them are close to harmonic. This indicates that in the practical that these things are designed to be very square and work out to be very linear. From the controls with regards to the linearities and non-linearities, as we read about from Gaussian, where he says, hey, sometimes you design stuff to just exclude these phenomena because otherwise there's no predictive power at all. Not that that's complete and consistent for an arbitrary and free-form sort of thing, but just it helps reach our sensibility, fungibility, and tractability. It's about what there is to it. The expansion of a complicated wave process into harmonic waves and the reduction of the problem to grad squared f plus k squared f equals 0, where the frequency is assumed to be already given, provide a most convenient method of analysis when dispersion is present. Velocity c is a function of omega. Dispersion is generally like, also it's always going to be radiating. They're the parasitics, so we kind of have to figure out what to do for the attenuative and dissipative because there's no free lunch. So at least we can kind of calculate the chit this way. In what follows, we shall consider harmonic waves almost exclusively, constructing wave excitations or more complex forms from them when necessary. So that's kind of interesting introduction to the plane waves, and it lines up quite directly with what comes up out of Coulson, and it helps to bring us like, well, this is why we have a Fourier-style analysis, because, and this is why we have this Gaussian-Eulerian analysis, because. This is why we have our theory of the Laplacians or harmonic functions, because. Draw a big circle around that. (1.2) In homogeneous plane waves, there's an interesting generalization of the expression for the plane harmonic wave that is important for further development. It was shown above that k sub x, k sub y, and k sub z are the components of the wave vector along the coordinate axes. The wave vector. It was assumed that we can choose any three real numbers as such quantities that satisfy the relation that the sum of their squares equals the numbers squared, this scalar value squared. We now give up the graphical presentation in the treatment of these numbers and assume that the set of k sub x, k sub y, k sub z is a triplet of complex numbers with k sub x equals k prime x plus I k double prime x, k sub y equals k sub prime sub y plus I k double prime sub y, and k sub z equals k prime sub z plus I k double prime sub z. I can only assume it's employing L'Hopital's rule and Rollo's theorem and what's called a method of linearization to express that the analyticity holds, that otherwise it's quite entirely dependent on analyticity vis-a-vis these linearizations. And L'Hopital's rule with regards to the derivative and the value of a thing, and Rollo's theorem. Here we again require that equation 1.9 be satisfied for real values of k equals omega over c. This is the only thing that has to come out of it is the value. Then the equation 1.7 will again satisfy the wave equation 1.8. Let's see what kind of a wave will be described by this with its complex values of these numbers. Substituting we obtain f equals, and he just kind of places what was in the value of how the wave number and the dot product, the inner product of this wave vector and the radius, or r, is, and that he just writes it out then according to the expansion of those terms as by their assignment, like so. This expression describes a wave with varying amplitude. The planes of constant amplitude are given by the equation k double prime x, k double prime in x of x times x, k double prime in y times y plus k double prime of z plus z equals c1. In the planes of constant phase, by the equation, this other one of k prime x sub x times x, or the sum of this imaginary extension after L'Hopital's rule equals C2, this other constant, where C1 and C2 are constants. So in the identity dimension, descriptive differential dynamics, there's quite a lot of talk about, well, what is a constant when it comes out of this, and what does it reflect in terms of that being just a pole or a singularity with regards to the stability and these kinds of things. he continues, we can show that the planes of constant phase are orthogonal to the planes of constant amplitude. So this is the very usual, most elementary notion of employing orthogonality for the separation of the components, and then with regards to you can treat each or the other, you figure, as fixed, and then otherwise with regards to that their partials hold, and with regards to the transforms, and then all such manners of the methods of analysis, what result for Fourier-style analysis, these things. Actually, is substituting 1.10 into 1.9 and equating the imaginary parts of both sides of the equation. See, after this is one of the dangers, because after the linearization or small angle approximation, they're considered the same, there's still quantities that are only defined in that manner. They're not zero. They're not equals. They're arbitrarily similar. But carrying on. Actually, in equating the imaginary parts of both sides of the equation, we get this k prime sub x times k double prime sub x plus dot 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 and y plus dot 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 and z equals 0. This equation expresses the condition of orthogonality of the planes, amplitude and phase. A wave of the form is usually called an inhomogeneous plane wave. This wave propagates in a direction given by the vector, and then the wave vector k prime of its partials in the wave numbers, and has an amplitude that falls off in one of the perpendicular directions. So this is kind of the introduction to the whole idea of the waves in layered media, because this is under the surface, the attenuation and dissipation. It helps capture the terms vis-a-vis the surface and the plane wave, and then what happens to it as it's so described in this manner. By an appropriate choice of coordinates can always be arranged that k prime sub y plus equals k double prime sub y equals 0. As long as it's not, turning around. Then, just as for ordinary plane waves, we can introduce a certain angle theta and set k sub x equals k sine theta and k sub z equals k cosine theta. For complex k sub x and k sub z, the angle theta will also be complex. For example, consider the case theta equals pi over 2 minus I alpha, where alpha is real. From these above, we get k sub x equals k hyperbolic cosine or cosh alpha, k sub z equals ik sinh alpha, and equation 1.7 for a plane wave is written f equals big psi omega times e to this quantity ikx cosh alpha minus kz sinh alpha minus iwt, or I times, and you can't really collect the term out of it, this imaginary term. It's attached yet to the quantities that then have this addition formula vis-a-vis this other arithmetic. This gets back into descriptive differential dynamics quite a bit, about the notion that these quantities are having implied units, and that the implicits must be kept in following these derivations, because they have their constraints. And so it helps affect the reflection for things like gimbal lock, or the affine transformations in what's otherwise free rotations. Why it's possible then to kind of look at these kind of things, and with the goal being to figure out how to have a descriptive differential dynamics of those, to later be able to say that a given development and derivation could, when it's possible to rewrite these things into like a theory of some potentials that's beyond harmonic theory linearly, but it still is true, what would be the necessary and needful to carry into these derivations to keep separate what needs to be separate, and put together what needs to be together, that otherwise in this sensible and fungible and deliberate and in what results a tractable way, that can all be discarded and this can just be computed. So this is why higher mathematics has a lot going on with regards to all the necessary and needful just to get to a simple statement of regular concerns in dynamics in all parameterized by time and space in these qualitative aspects of these quantitative things, and how to be able to keep reusing that theory instead of wallpapering on top of it the fixes, pasting it together at the edges that are falling apart. This wave propagates in the x direction and falls off exponentially in the z direction. The velocity of propagation of the wave is equal to c sub x is on the order of omega over k sub x equals c over cos alpha as follows from 1.15. So for this, then it gets into all the kind of the actions of the relations of the identities of the trigonometric functions and the hyperbolic trigonometric functions. And they're great facility. And then for the fact that in every single math library in the C runtime in all the computers in the world that such functions are implemented and available for the compute part. That is, the velocity is always less than the velocity of propagation of an ordinary plane wave C. Its radiation C is its own attenuation. Corresponding wavelength is equal to 2 pi over k times cos alpha equals lambda over cos alpha, i.e. it is less than the ordinary wavelength at the same frequency. The larger alpha, the smaller the wavelength, and the larger the attenuation coefficient of the wave in the z direction. See, these are the sort of theorems then result later qualitatively how to get after these ones and then say, hey, we've used these formulas at least to establish then that these qualitative properties hold, so that later when we're trying to figure out what's going on with it, we're actually going to first lean on these qualitative properties because these are the ones that we hope will actually kind of reflect the real behavior of this thing, regardless of the fact that otherwise it would kind of get jimmied in the middle, vis-a-vis these kinds of things. All the above refers to the case of the absence of absorption of the wave in the medium, real K. The introduction of the concept of inhomogeneous waves in the presence of absorption does not present any fundamental difficulties. Here the planes of equal phase and equal amplitude are no longer perpendicular to one another. We also note that the introduction of the concept of inhomogeneous plane waves is not valid for an unbounded space, since the requirement of boundedness of the field at infinity is violated. In what follows, we shall make use of this concept in the case of semi-infinite media. Running ahead a bit, we shall show that inhomogeneous plane waves can transform into ordinary plane waves and vice versa in the refraction of plane waves at an interface. So here he starts to define the reflection and refraction according to these models with regards to not quite being optical, that's acoustic largely, all these models. With regards to these waves, the propagation of waves, and the radiation of waves, the attenuation and dissipation of waves, with regards to the oscillation and restitution of waves. This is seen directly from the refraction law, n sine theta 1 equals sine theta, where n is the index of refraction, theta is the angle of incidence, and theta 1 the angle of refraction. If n less than 1 and sine theta greater than n, then it follows from that formula that sine theta 1 is greater than 1, i.e. theta 1 is complex. Because sine ranges from 0 to 1, right? i.e. theta 1 is complex and the refracted wave is inhomogeneous. So here it helps describe as actually we just kind of kept our mathematical attached here for a second and notice that the product carries an product space to an outer product, vis-a-vis the usual great application of inner products to find significance and the trace and this kind of thing, the determinant. The refracted wave will be the ordinary homogeneous one. On the other hand, if sine theta is greater than 1, i.e. if the incident wave is inhomogeneous but sine theta less than n, in this case, of course, n greater than 1, we then get sine theta 1 is less than 1, i.e. the refracted wave will be the ordinary homogeneous one. Both these cases will be encountered in section 32, where the refraction of spherical waves is considered. The spherical wave can be expanded into a set of plane waves, including inhomogeneous plane waves. Well, so that's kind of interesting, and it kind of brings us up to page 5 on Berkowski's book here on waves and layered media. And there's only about 100 times as many pages as that with regards to then it makes the derivations and developments that really fill in all these kinds of things that come on and go on with it. This book by G.A. Mogan, I really enjoyed it because what I got into is an approach to field theories together, and their linearities with respect to one, and internally and across with respect to each other. E cross B, Maxwell's law, with respect to each other, then show all the non-linearities and linears with respect to that they're inhomogeneous to each other, they're heterogeneous to each other, or inhomogeneous to each other. And so these are the kinds of things that go into a lot of the definitions. But he gives names, names for the Rayleigh waves and Stoney waves, love waves, surface waves, and all such manners of the descriptive elements, the description of what get into these things, vis-a-vis, as we're just talking about so far, we're talking about plane waves. And after Coulson's theories of waves, of functions that define waves, wave functions. And he gets all into the near field and far field and Poincaré. And so after Gauss and Euler, then and analyticity, then we're going to talk about Poincaré and perturbation and Poincaré's rough plane, and what that means then with regards to things that make for approaches for the analysis situs, as for Poincaré and Lefschetz, that are more important and relevant for algebraic geometry than for Gauss and Euler and Euler's identity and the algebraic geometry. So anyways, that's about it for today, I suppose. I shall still hope you have a great day, and that the time has been pretty good. So let's see, what else to figure out for that? So that's for today, the idea is just kind of get an introduction to waves and layered media, and to just kind of talk into the description of waves by their mathematical formalisms. And then what I got into was a lot of the available conceptual settings here with regards to the Fourier-style analysis, with regards to the Eulerian and Gaussian, with regards to those and the trigonometric setting, and then with regards to the qualitative or descriptive elements of waves, and then a lot about, for the descriptive differential dynamics, what are the what are quantities vis-a-vis our attachments to algebra and arithmetic, and when it can be reached to where then that can all fall away as a stroke and just kind of a computation vis-a-vis the necessary tent, the framework as what can, this superposition of concept and derivation, where the usual notion of superposition is like all the possible elements that could add up to any given one, they all solve. Vis-a-vis, it's like all together, this is only one derivation, and it just reduces internally to the solution. The inner and the outer, and its complement the outer and the inner. Hey, I shall so hope you have a great day today.